All right. So in this particular example here, our aim is to find the equation of the elastic curve, right, and the maximum deflection. This here, we know what we should do to find the equation of the elastic curve. Here is the problem, right? The example we did initially was find deflection at A or B or something, right? But here it says maximum deflection. Here is when the process comes in, right? So looking at this very well, if we do a very body diagram, it's of this. So we have this, we have A, and then we have B. These are points, right? But this problem can be seen in a different way, but also mean the same way. Right? I'll talk about that later on. Right? So we have the linear distributed force, right? Acting on the whole length of the beam, right? The whole length is F, right? Looking at this, we have a reaction here, reaction at A, and then we have a reaction at B, right? So let's even resolve this. So the sum of the forces in the y direction should be equal to 0, meaning that this is a distributed force and it's acting on the whole length. So in terms of forces, to be this way to W x, right? Then all this should be equal to RA, right? We need forces here plus RB. When you look at things, you can see RA and RB are the same, right? So I give you the same upwards reaction, right? So then we can see this all equal to 2RA. Right now we have this. We see clearly that uh, we see clearly that this actually x here. The whole length is x. So the force times the whole length x, right? See clearly that RA is equal to WL on 2, right? So this is what we have, which is the same as RB, right? So now that we have what do you call it, the reactions, we go on to find the equation of the elastic curve, right? So here we will do a moment balance. But before we even do that, we look at this and then we see clearly that we can only do 1 second, right? One second will also help us. So we have this. We are doing do everything from left hand side. So this our point here, this is our shear force, and this is our moment, right? We have reaction RA here, which WL on 2, right? And linear distributed force. This one time about linear distributed. Now that we're bringing it onto a section like this, and we are bringing it onto a section like this, where the whole length here is x. Right? We know that this linear distributed is usually considered adjacent, right? So if we're to here, it will be kind of maybe the midpoint midway somewhere here, which where x is equal to L onto per coordinate system, right? This coordinate system x, y, right? This is coordinate system for this is 2, right? 2, right? So then this how the will be. It will be somewhere midway of this whole length of x of this section here, right? So if b is somewhere here, we can start the distance we get to here is about half the distance of this whole x, right? So from here to here, this distance here, let me this distance here is about x on 2, right? And then this w here is acting on the whole x, the whole section 2x. So this is the force because it's a linear force. Because here it's just saying there is depending on distance. It's saying acting on the L, but here it's acting on the whole section, right? So the moment about the point D, the sum of the moment at the point D, right? So we know that the moment, the sum of the moment at the point D is 0, right? So if you're doing that balancing moment, you get M, right? Plus we have 4, now we're going in this direction, this way, right? So we have W x, right? And this distance is what x on 2, right? And the one on the other side is W L on 2, which is the force. This distance is x, right? So this is what we have. But then we know E, so it's I M here, so M here to be E I, right? Y second derivative plus this. So if you make that subject, it becomes W L x on 2 minus W x squared on 2, right? And then our aim is to do what? Is to find the equation of the elastic curve and the maximum deflection, right? Now that we have this, there's something that we must make clear. So if this the beam again, this is the initial point, right? And these are points A and B, right? If we apply that linear distributed force, it will reflect this way, right? So we know the whole length of this is right. But then look at this, because the linear distributed force, the deflection will just be at the center somewhere, which is midway between, right? So the maximum deflection that we're looking for will be midway between, right? Which is where this is where our coordinate system x will go to L2, right? Let me write this one. L on 2. So this is where our maximum deflection will be here at this point. Right. So it's the same of saying, so that same question can be said that can be reframed and said that find the deflection midway, right? Or find the deflection between A and B. The same as find deflection, the maximum deflection, right? It's the same thing. It's said in different ways. If the point is not actually correct, right? So I aim to find deflection, right? So meaning I have to do double equation to get y, right? Deflection at L is equal to S on, sorry, deflection at S is equal to L on U, right? So double integration, if you can do it for it, fine. If you can't, you can do it step by step. You still get C, right? So let's see. So this we get E first integration. Right? Here we are doing step by step. I like E first derivative is equal to W L x on 2 on 4, right? And then we have minus W x, right? To the power 3 on 6, right? Plus constant integration, right? When we do second integration, get E I y just y, right? And we get W L x to the power 3 on 12 minus W x to the power 4 on 24, right? And then this becomes C1x and this is C2. Yes. Now that we have this, because our interest is in finding y, it's appropriate to make y the subject and then find constant. So let's make our work easy. This y here, right? Y will give us 1 on E I into bracket W L x to the power 3 on 12 minus W x to the power 4 on 24 plus Cx C1x plus C2, right? Now it's time to find a constant, right? But then make our work is that when we find a constant, we use this particular one. Let's label equation. See. Let's say this is equation 1. This is equation 2. Right? Yes. So let's see what we do. Now our aim is to find constant, right? But looking at the big game, we have to take boundary conditions. There are two sets of boundary conditions, right? So we have to be this way, right? We point A, point B. Let me use a different color, right? And then it's reflected, right? At point A, because our coordinate system is this way, here's y, and then here's x, right? At this point here, at A, we have x equal to 0, and then because we're finding slope y, right? Depends on what again? We are trying to find a constant, right? So the only thing that change here is x, right? And then y. So we have to find a condition for x and y, right? So looking at this, at the point A here, which is here, our x is 0, and then our y, there is no division at that point, it's 0, right? At point this point B here, we have our x equal to the full length of the beam, right? And our deflection is 0 here too, right? So these are boundary conditions, the two sets that help us find the constant, right? So this is already, which will pick one. So we are picking the, let's see, let me something else, alpha something. Let's see. There's no need to write them when you're doing, but this, so we can follow, right? Yes. So this boundary condition set alpha one constant beta. Right? So now we are using alpha, right? So for the same equation, to find a constant. So here we are saying that x is y is 0. So when we put it in this equation, let's see. Let's copy this. Yeah, that's fine. Okay, this we have. So when I put this one here, this equation, let's see what we have. E I and plus bracket 0, W L x is 0, the power 3, 12 minus W power 0. So we continue. It will be minus W x is 0, the bracket 20, this is 4, right? Yeah, minus 4. That's 24. 24 plus C1, we know x is what? X is 0, and then C2 is only remaining. So meaning from this we find C2. 0, 0, 0, 0. Meaning this implies that we have C2 to go to 0. Right? Now, the aim is now to find, now we know that this is out. This C2 is out. The next step is to find C1. Right? The C1. Let me write it. This C1 X. Now we use the second set of boundary condition, which is this beta, to find a C2. Right? So let's do that. Beta. Now we have this, and then we know that C2 here is actually 0. Now we put the set 200 conditions to find out where is it. Is it? Which is x is equal to L y 0, right? So y 0. I don't need to write this out always, but I'm just writing this so you can follow. W L is just L, x is L, it's about 3, and then we have 12, we have W, bracket L, on 24, 24, right? 24. Plus 0, we have C1 into bracket L, right? Now aim is to find C1. So know this is 0, everything becomes 0. Now I find C1. So we're trying to simplify this. Let's see. C1 L, right? C1 times L is equal to W L 24 minus W x to the power 4 on 12, right? All this is equal to 124 minus 1. There's a mistake. WL. Let's see. I'm missing something. 3 WX. You see? That's very far. If I read right, this is x to the power 4. This is x to the power 4 here. X to the power 4. You miss one, then the whole thing is different. So in this case, it's much more appropriate if you put them in brackets, so you know there's something that you wrote there earlier. Where it becomes much more easier for you to power 4 here, right? The power 4 here. So 1 on 24 minus 1 on 12, that's about 124. So let's see. Let's see. 1 on 24 minus 1 on 12, right? So that's 1 minus 1 on 24. Right? Minus 1 on 24. Right? So you end up getting WL to the power 4 minus 24. Now, look at this. right? Now that we have this, we're trying to find our C1. So our C1 will be minus WL to the power 4 all up to 4L, which we end up with minus WL to the power 3 124. Right? So now we have our C1. We put that back into equation, what's it? Into this one, the original one, and then we make y the subject, right? This particular one here. Let's label it. Let's see. Let's get 5. We don't know what's going to be. This is equation 5, right? So we're now putting our constant, putting back into the equation. So we're putting the constant that we found back in the equation. You know, here is 4, right? And I'm trying to put this. So we get E I Y is equal to WL x power 3 on 12 minus W x power 4 on 24. Here's to 4. Right? Plus, you know, C2 here is 0, and we know C1 to be minus, right? So minus WL cubed 24 all times 4 x, right? There we have. So let's see. Okay, we'll have our y, right? Our y now will be an E I, right? We have W L x power 3 small minus 4 the W x power 4 C 4 minus W L to power 3 times x on 24. So now that we have this, we can go ahead and find our y. When x is equal to 2, which is same as saying finding the deflection, the maximum deflection, or the deflection between A and B, or deflection midway in the beam, right? Yeah, so that's what we'll do. We'll get 1 on EI, 1 on EI. On an EI, W, L, X is on 2, Q on 12, minus W, L on 2, so power 4, 24, right? And then we have minus W, L cube times L on 2, right? W L cube times L on 2, right, on 24. So now that we have this, now we have this, we are just to simplify everything. So we end up getting 1 on EI brackets W L to the power 4, right? And you get 1 on the power 8, 1 on the water power 8 divided by 4. So let's see. That's 1 on 2 to the power 8 divided by 12. That gives 1 on 96, right? So that's 96. And then we have this is 1 to the power 4 24. 2 to the power 4 24. It's 1 on 384. A view L to the power 4 to minus 384. Then we have just this, so just 2. 1 on 2 divided by 24. That gives us 148. So we have the view L to the power 4 on 58, right? 58. So this is what we have now. When we try to factorize, we have W L to the power is 4 actually. It should be 4. Let's factorize the power 4 on EI. So we have 96, 34, 48. Let's see. 196 minus 134 minus 148 minus 534. So this I have a minus 5.384. So our final answer was minus 5 WL to the power 4 on 384 ER. Yes, this is my answer.